Hello everyone. In today's class, I will be talking about Introduction to Software Engineering. The agenda of today's lecture starts by the definition of the software, in addition to software engineering and its scope. We will go over fundamental definitions of software problem and its major forces, including cost, schedule, and quality. After covering the software problem, I will go over the software development process and explaining the entire software lifecycle. Finally, I will address the common process models that are used to model a software process, including the waterfall model, the prototyping model, the iterative model, the time boxing, and agile process models. So let's just start by a definition of a software. What is a software? As you know, this course is mainly about software requirements and specifications, so which is a major component in a software development process. So at the end of the story, we are trying to develop and design a software. So in our field, in software engineering, we consider a software as a collection of executable programming code associated with libraries and documentations. As you will see later, in developing software, we have to perform multi-phases process. At each process, we have associated libraries and documentations that will illustrate the functionality of each process in terms of the input of the phase and the output of each phase. When we use the word software, that means, especially in industrial applications, we are seeking large, robust, reusable, and evolving softwares. The reason why we study software, let's think about the number one reason, is because it actually in this course, it focuses on the fundamental of the design. So it teaches you how to design. That's why we study software. In my course, we are addressing a software requirements, so which is a prior stage before a software design. So we will start first by addressing how to collect the requirements and analyze such requirements and then specify the requirements. After the requirement phase, here comes the design phase. That's why you are studying software. In addition to the capability of designing and analyzing, you are also provided with skills related to problem solving, because when you collect requirements from the customer, it's your task to find a solution for the requirements to build a software that would satisfy the customer needs. Let me introduce to you some common software systems that are currently available in our everyday life. We do have system softwares. An example to those system softwares like compilers, editors, file management utilities, all of these are considered as system software. We also might have some standalone programs, especially that are designed for specific needs. We call them application software. When we are designing and implementing scientific related algorithms related to either engineering or science, we are referring to engineering and scientific software. If we are building and developing software that will actually reside within a product or even entire system, we are talking about embedded software. The group of software that would actually focus on a limited marketplace in order to address massive consumer market, we call this group the product line software. A little bit of sophisticated, other sophisticated software that are built in sophisticated environments. We call most related to web and network centric software. And they are very sophisticated, especially if they are built in complex environments that are integrated not only on the level of the software itself, but it's also integrated remotely with database, business, and applications. Finally, there are a very well-known group of software that we call it intelligent systems. And this mainly we refer to the software that uses non-technical algorithm to solve a complex problem. Example of intelligent systems include robotics, expert systems, and better recognition. Let me add to this, we also have machine learning intelligence systems. So the machine learning algorithms is considered as intelligent system. We also have some smart city algorithms or software. So we call it intelligent system. Any software that uses non-technical algorithms to solve a certain complex problem in an automated and intelligent, smart way, we will refer to it as intelligent system. So after we learn a little bit about different type of software systems, so we need to understand what is a software engineering. There are many definitions of software engineering. In this class, we will focus on the definition of the IEEE standard, which state that a software engineering discipline is the application of a systematic, disciplined, quantifiable approach in order to develop and to operate and maintain a software, which we would consider as at the end as a product. This is in particular the application of engineering to a software. So engineering include systematic, disciplined, and quantifiable methodology to develop a product. So when it comes to software, like we say, software engineering, the application of such systematic and disciplined, quantified approach or methodology in order to develop and operate and maintain a software to have a product at the end. This is the IEEE standard definition of software engineering. Aligned to the definition that is defined by the Canadian Standard Association, software engineering is defined as the systematic activities involved in the design, implementation, and testing of a software to optimize its production as well as its support. So this is another definition of software engineering defined by the Canadian Standards Association. In this course, we're going to use the general definition provided by the IEEE standards, and then with the focus of what the Canadian Standard Association has defined as well. After now we understand what is a software engineering, let's go a little bit and try to understand more or dig more into the scope of software engineering. Keep in mind that you try to engineer a software to provide a product at the end. So the scope of software engineering is not on small scale systems. Software engineering is part of a much larger system that would include a lot of design activities. Example of systems where software engineering is a huge component, is a big component. And we could see software engineering applied in telephone switching systems, banking systems, hospital administration systems, and of course, aircrafts. One thing that you should always know that can we always perform software engineering in the right procedure that would generate a high quality product at the end? That's a big question, and it's a great challenge. So in order to perform a software engineering in the right procedure, that definitely would require a much larger look or like a deeper investigation to the system engineering issues that might arise when we apply or perform software engineering for the larger systems that we are dealing with. The engineering issues that we might need to investigate or provide a much larger look at include entities and activities within the system, as well as the interface with other systems and users. In addition to this, we might also look at the boundaries between the entities and the activities, whether they are within the system or with the interaction with the interface of other systems and users. Understanding the application itself And the user need is a key attribute in software development. This is very important to know that when it comes to the development of a software, by applying the fundamentals of software engineering to guarantee a high quality product at the end, one major attribute in such a development process is the understanding of the application itself and the user needs. With this, we need to decide on what activity should be supported by the system and how to understand the application itself and the user need. In addition, keep in mind that there are many domains where very different software systems must be developed. However, it might be aligned with different level of priorities. For example, in telecom applications, the time to market is of high priority. In aerospace and NASA shuttle applications, the safety is of high priority. In telecom and banking applications, the maintainability is of high priority. So software engineering is applied in much larger system frameworks. It requires a complete understanding of the entire problem and with capability of designing a software of high quality. And in such way, we have to know what are the requirement of the users, the requirement of the customer, as well as on a full understanding of the given application. Some applications or software systems that are developed, they are developed on priority levels, and this has to be addressed within the software engineering process. So in developing software, there is always what we call the software problem. The software problem is the major problem that most of the software engineer, or in general all the stakeholders involved in the software development, are facing, which would be defined by three main forces. The first one is the cost of a product, like how much are we going to pay for such product and is it within the budget or not. The second one is the schedule, like if there is a tight schedule by which we would like to develop the product or the software within the schedule, that's another issue. And third is the quality. We would like to develop a software of high quality. Combining the cost, the schedule, and the quality would define the software problem. So software problem. So if you'd like to define, what is a software problem? Is a composition of three main forces. The first one is the cost of the product. The second one is the schedule. And the third one is the quality of the product. Now, let's investigate each one of those forces individually and see how each of those factors will actually impact on the solution of the entire software problem. The first one is the cost. If software is really expensive, maybe we compare it to the hardware development. When we compare software to hardware, is it really expensive? Let's have a look at this. Let's look to those set of costs, whether it's direct or indirect costs that are involved in the development of a software. So we use two factors to define costs in software development. The first one is the LOC, which stands for lines of code. The second one is PM, which stands for person per month. The standards is normally we are looking for assigning 1,000 line of code per person per month. If we assume that per line of code, we are paying $3 to $10. So roughly software costs will range from $3,000 to $10,000 per person per month. That means each line of the delivered cost will actually cost a lot. A simple application for a business may have 20,000 line of code to 50,000 line of code, If we do a little bit of calculation of the associated cost based on the previous assumption, that means we are looking for cost of $100,000 to a range of $2.25 million. This is really costly. So to build a software that will cost from $100,000 to like millions of dollars, like traditionally or typically would be running on hardware that would cost any number between $10,000 to $20,000. That means hardware cost in any IoT solution in software development are way small as compared to software costs. So software is really expensive. So you have to, as an industry firm or industry enterprise, you would like to build a software. You have a team of software developers, software engineers, and then you would like to guarantee that your software cost is within the aligned budget of the customer. The second component or driving force that make the software development a major problem is the schedule. Software would always require a tight schedule. Business requirements today would actually demand short delivery times for delivering or developing a software. Over the past, we were able to see that software products have often failed to be completed in time. That was not good because now we are not satisfying the customer need. Neither the software is provided in an accurate time frame that was agreed on the first meeting with the customer. So we say that those software products have failed to be completed in time. So we have now one problem as part of the entire software problem paradigm. So based on this, now we understand that it's not only about building a software with less cost. The cycle time also is a fundamental driving force. So for us to build a software, we need to guarantee that it's cost effective and it is within the scheduled cycle time. It has been delivered within the right schedule or the scheduled cycle time. For the cost and the schedule, both of them actually could be quantified to a number, and this number could be used to assess on the overall, I don't want to use the word quality, but I would say the overall productivity of the product. So they have combined cost and schedule all together, and they use the word productivity to refer to products with high productivity or products with low productivity. The definition of productivity is just the ratio between the output to the input resources, where in software systems, output is considered as the set of line of codes, whether they are on thousands line of codes. We use the KLC for thousands of line of code. And the input resources, simply they are defined by the efforts per person per month, the overhead cost modeled in the rate for each person per month. So for each software product, once you take the ratio between the output to the input resources, then you have a number, you have a measure. This measure is called productivity. If after the fact you calculate the productivity of your software and then the productivity is high, that means we are seeking or we have a product of lower cost. If we have high productivity, that means that we have a software that is of lower cycle time. So always when you build or develop a software, you are seeking higher productivity in order to reduce the cost as well as the entire cycle time. So for projects to deliver software, now we have quality of a software, as well as productivity, where productivity is a combination of the cost as well as the schedule, are becoming driving forces or drivers for software development in large scale projects. The third driving force in software development is software quality. Along with productivity, we know for sure that quality is the major driving force. Developing high quality software is a basic goal. We're always looking for softwares that are of high quality. However, defining software quality is a little bit harder to define. Like there is no definition of the word quality. Like we cannot say what is the definition of a quality of a software. Can we quantify it by a number, and then we're going to use this number to claim that the software is of high quality or not? It's really hard to define or quantify. So using the ISO standards, we use 6 attributes to identify the quality of a software. Multiple dimensions, which means we have 6 attributes, so we are not using just one feature or one attribute to describe the quality. In other words, we don't say efficiency is a measure of quality. When you use efficiency only, that's one dimension attribute, but it's unfair that you're going to use efficiency only as an attribute to determine the quality of a software. Using the ISO standard, you have to use the 6 attributes. You might use 1 or 2 of them, or you might use all of them. It depends on the project itself. That's why multiple dimensions would mean that it's not easy to map the quality to just a single number. We cannot just say it's 60% of quality because the efficiency is 60%. I can't say this. It's multiple dimension quantification or multiple dimension performance analysis. So we cannot just use one number to represent the quality. It's mainly based on each project. So the concept of quality is project specific. For some projects, maybe reliability is the most important attribute to describe the quality of the software. In others, on other projects, the usability might be even more important. In some applications, we might even combine all of them. So the 6 attributes that we might use to describe or to assess the quality of a software include the functionality of the software, the reliability of the software, whether it's usable or not. So the usability of the software, the efficiency of the software, the maintainability of the software with less that means we are seeking less bugs and defects all the time. Portability of the software means if it could be portable across different systems. In some major projects, reliability is commonly used as a factor of quality. In some other projects, you might use usability. I have seen a lot of complex projects where the efficiency and reliability, functionality, all combined are used to judge on the quality of the developed software. Generally, reliability is considered as the main quality criteria. Most of the software projects, they use reliability as the main quality criterion, and then they add any other quality criterion to the reliability. So in summary, the software problem would include cost. How would you optimize the cost of your project? By optimizing the direct cost for each line of code. So the cost is calculated or measured by line of code and the dollar amount per line of code per each person per month. So the cost is quantifiable. Like I could find a number to describe my code, either $100 or $1 million. It's quantifiable. There is a measure for the cost. And my task as a software software developer is to guarantee that software developer with the software manager and the entire stakeholder team is to guarantee that the entire cost allocated to the software is within the budget. Also, the cycle time is quantifiable or could be measured. So could be measured, the schedule could be measured by just calculating the cycle time. And then keep in mind it is fundamental driving force. So you have to keep your cycle time within the schedule of the software. Combining the cost and the schedule, we have the productivity, the ratio between the output and input resources used. Our goal always in a software development process is to guarantee that we have high productivity to reduce the cost and the cycle time. The so the quality, on the other hand, is defined by the six attributes, and the quantity cannot be measured or quantified. I can't say it's a 60%, 7%. No, it is across multi-dimension. So quality and productivity together, they are the basic driver in a software project. The aim of most methodologies is to guarantee that the delivery of the software is with high quality and productivity. Besides the need to achieve high quality and productivity, there must be some other needs based on the customer provided needs as well as the user needs. So, in summary, when you develop a software, you might get stuck in the software problem in which you would like to guarantee that the cost is effective, the cycle time is within the schedule. That means we're seeking high productivity and we are developing a software of high quality. So now after we define a software followed by software engineering, and we summarized a software problem across the three main forces, who are the stakeholders in a software development cycle or process? In software production, we do have customers. Customers or clients are those people who wants the software to be built. And actually, they often don't know anything about what he or she might want. They have a lot of things in their mind that they would like to deliver to the software requirements engineer, but they just say, "I want to build this," but they don't know how, like, what the main requirements that would be easily transferred to the software requirement engineer. They do have a lot of things in their mind. Maybe they cannot express it well, uh, which makes the job of a software requirement engineer very hard because now the requirements are not well defined or understood. The second set of people who might be who are involved in a software production process are managers or designers who actually plan the software. We know that it's really hard to foresee all the problems and issue in advance. So managers, they work so hard in planning a software. That means they have to keep track with most of the problems and issues in advance, but it's really hard task. So they most of the time is consumed or wasted for the planning part of the software. We also have developers who are going to write the code to implement the software. For larger system, it's really hard to write complex code for larger systems, so that's a little bit tricky. And then we do have the testers who perform the quality assurance. Because it's really impossible to test every combination of actions, the tester, they have to perform a critical task to identify those errors and defects in the software across all the phases of the software development process. So it's also their task is very challenging. Finally, we do have users who gonna purchase and use the software product, and a lot of some of the challenges that we might face after the fact we have deployed the software which is ready for production now, that we might face the situation where users could misunderstood the product. So you have to consider before releasing your software that it's easily understandable by the end user at the end. Um, Now, I would like to define software development fundamentals, because at the end of the story, we will focus on the requirements of software development. But because it's one component underneath the big umbrella of a software development process, there are some fundamentals that we need to cover. The first one is, what is a process? So when I'm going to use the term process in our class, I'm referring to a particular method, generally involving a number of steps. A process is a collection of activities or actions or tasks that are performed when some product is to be created. This is the definition of a process in general. When we are referring to the software process, we are referring to the set of steps or activities, along with ordering constraints on execution, to produce not just a product, to produce a software with desired outcome. Keep in mind that many types of activities performed by different people. We have developers for software development, we have testers for software testing, we have software requirements engineer for requirement analysis and specification. So the different activities along the way in the software development process, we see that are performed, those activities are performed by different people with different skills and qualification. Software process is comprising of many component processes, so it's not just one process. We will see that software process is comprising of many phases. Each phase, like requirement analysis, like design, and then we do coding, and then we do testing, and then we do maintenance, and then we do deployment. So it is not just one process, it's a collection of processes. It is many component processes all together are used to define the entire software process. So in software development process, the word process is different from the word product. When we use the word product, we are referring to the outcomes of executing a process on a project. Software engineering would focus on a process, not the word product. Proper processes are those processes that are developed to deliver software product in three factors: timely manner, within project with sufficient quality to satisfy clients and end user. That means high quality and productivity. So we would like to generate or to develop softwares with proper processes to guarantee that the software product is actually developed in within the schedule. That means it's in timely manner. It has sufficient quality to satisfy the client and the end users, as well as high productivity. So what are the key processes in a software development cycle? In software process, we have two major key processes: either a software development process or anything else. So in a software development process, we have another key processes. The first one is the engineering process and a project management process. So in our course, we are focusing on the software development process. We are focusing on the engineering software engineering component. Underneath it, we are focusing on requirement analysis and specification component. Other processes that we see in a software process would include configuration management, change management, inspection processes, and process improvement procedure or process. So let's now focus more on the engineering process as well as the project management process. The two major processes that we see in a software development process are the engineering, which means that we are seeking the development and quality steps to be performed, and will be assigned to engineer the software. Project management, on the other hand, refers to planning and controlling such development process. So in engineering, we are developing the software. We try to align with the quality steps that are needed to engineer the software. Planning and controlling over the developed process, the entire development process, this is the project management. Key rules in the software development process include developers who will execute the engineering process, including the software architects, the lead developers, and so on. For project managers who are responsible on managing the entire process. So these are the key rules that, or people or like stakeholders that are involved in the software development process to align with the two major processes, including engineering and project management. That means we are working with engineers and project managers. In a software development process, you have to be careful on major fundamental knowledge about it is when you are working on small project, like we working on a small scale projects, the software development method as well as the project management are performed on informal levels. So on the other hand, large complex projects are performed on formal development method and formal project management. What is the difference between formal or informal? For large complex projects, the development process has to be done in systematic and structured way. This is formal process. Informal process, that means we don't have to perform the development process in the same way that it should be structured. Like you don't have to do requirement analysis and then designing and then coding and then we do testing and then we do maintenance and deployment and then documentation. And like the entire process could be done without any formality or a systematic way. This is on the level of the development as well as the level of the management. If you work on large complex projects, both the development and the management should be done in formal methods. We should be stick to the typical standard structure systematic way of development and management. But if you're working on small scale projects, this is not necessarily. So in developing software, we need to know what is a software development process. So we talked about a software, we talked about a process, we talked about software process. Let's now talk about software development process. So we are referring to the process in which we are actually developing the software. As I said before, it's not just one module. It is a set of module or set of phases. And each phase is just a sequence of steps. For each phase, there are a variety of methodologies that are used to satisfy the functionality of each phase. And each phase would simply correspond to have different sequence of steps within such phase. Why we have phases? Because it's really good in modularity. It's really good in feedback recognition. Dividing the development process into phases is also very good for error tracking. It's really useful for the maintenance. So we can see that dividing the problem into a module, like by divide, like for we call this divide and conquer. When you are within a phase, it's easy for you to validate the phase, test the phase, to verify the phase, to provide any feedback about such phase. But if you see the entire process at just one module, it's really hard. So the feedback would not be easy to retrieve. It's really hard to track the error within one big process. And as you can see, like in programming wise, when you have used object-oriented programming before, where we encapsulate the data into objects, that's another way of modularity. Why would we do modularity? So we make our error tracking easy. We are working on multiple modules. They could be done in parallel in a way, or could be done in a sequence in a way that makes the feedback and transition between the phases much easier, which at the end will help in the maintenance as well as the deployment of the software. So to complete what I just said, it helps in the divide and conquer procedure. Each phase will handle different parts of the problem, and also it helps in the validation. What are the main activities and phases? Now we said a software development process is not just one phase, it's not just one module. A software development process is a multi-component process, is a multi-phases process. So commonly, it has the following 5 activities or phases. A software development process would start by requirement collection, analysis, specification. And the outcome of this phase will be the specification documents. So we do have the requirement specification documents. And then after we collect the requirements from the customer, we analyze it. We provide a specification about those requirements. We have generated the SRS document. So this is the specification requirement document, the SRS1. We go to the design phase, in which we actually build a design for the software. So it could be initial design, it could be the entire design based on the process model that we're going to build. So the design phase is considered its input from the requirement analysis phase, and it generates design documents at the end. And then after the design phase, we now have completed the design of the entire software. So we will code it. So the outcome will be code, of course, an optimized code. Now we're gonna take this code, we will send it to the testing phase, where we actually would have test documents. I'm gonna share with you more details about each of those ones in the next slides. Finally, when we test the software and all the defects have been identified and eliminated as much as we can, then we deliver or deploy the software. These are the typical or the commonly used activities or phases to describe a software development process. So in a basic software development process, as I said, we start by requirements, following design, and then after the design, we do have the coding and the testing. So we like implementation, which refer to coding, and then testing, and then integration as part of the programming paradigm. Finally, we have the delivery, and before delivery, we do have the maintenance. In the design phase, we call it the software design paradigm, in which we have to identify the software design models. So for each software design, you have to define the corresponding design model. In the coding phase or testing phase or integration phase, we are in the programming paradigm. So in a programming paradigm, it depends on the programming language that you're going to use it, whether it's procedure programming language or object-oriented concepts, or it's a logic programming language, or your programming paradigm is just functional. Keep in mind that along the way, the outcome of each phase is also aligned with documentation. We might have planning documentation, design documentations, requirement documentations, maintenance documentation. So along the way, we always have documents. Let's start now by the first phase in software development cycle, which is requirement analysis and specification. The core of this course will focus mainly on the requirement analysis and specification. So I will introduce it here briefly, but we will go over this across the entire semester. What do we do in the requirement analysis phase? We have to state the problem precisely. We know that it's really hard task. It needs a lot of understanding about what the customer need is, what the customer would tell, and then what the software requirement engineer and have understood from the customer. We know that the requirement analysis forms the basis of agreement between the user and the developer. Requirement specification, even for for medium systems, could be 100 of pages, like the SRS document. The requirement specification document could be of 100 pages. So in this phase, we care a lot about what, not how we're going to design or how we're going to develop the software. We just care about what the customer wants. What are the customer needs. So we have to state the problem very precisely. We have to understand all the fundamental questions related to what are the customer needs, what are the software requirement, what are the functionality of the software, what are the interface that the customer will need it, what is the cost that the customer will need it, who are the users, and what platform they will use this software in. A lot of what questions should be answered in this phase. The output, as I said, is the SRS document, which is the software requirement specification document. So you will see that after each of those phases in the software requirement process, we always generate documents. Why requirement analysis is really crucial, a really crucial phase. It's really a key factor in the entire software development process. Let me give you an example to show why. So collecting requirements might even affect of the entire process. So we might end up in developing a software that actually was not what the customer wants. So assume the requirement specification was done on this shape, like the customer would like to have a swing on a tree. And then when we collected the requirements, and then when we specified those requirements, we were able to, as a requirement engineer, to just assume that it should look like this in figure A. However, when we transfer this information to the developer understands it, which is different. So now we can see in the way that the requirements were specified. When we send it to the developer, the developers understand it in a different way. And then this is how the problem was initiated, solved as in figure C. If we look to figure D, this is how the problem is finally solved. And then in a debugging phase, we can see figure E, which like they try to debug and remove some of the errors, because how are you going to do the swing actually, because you are facing the tree right now. So you have to cut the tree. So this is how the program is described by the marketing department, which is completely not what the customer wanted at the beginning. So you can see collecting and specifying requirements in a way that was not completely understood. So we don't have high quality requirements that ends up at the end that we have built a software that is completely different from what the customer wants. And that's why requirement analysis as the first phase in the software development process is a very crucial task. It's very critical, because once you've done the requirements, you're gonna do the design, and the design is mainly built on the requirements. So if you have poor requirements collected or analyzed, that will end up to software of low productivity and low quality. The second phase in a software development cycle or software development process is the design phase. In this step, we are moving from the problem domain into the solution domain. So in the requirement analysis, we identify the problem. In the design phase, we actually moving from defining the problem to find a solution to the problem so by designing the software. There are three main tasks that we perform in the design phase, including the architecture design, the high-level design, and the detailed design. In architecture design, we have components and connectors that should be in the system. In high-level design, we have more high-level understanding of the design of the software. So we do have module and data structures that are needed to implement the architecture. And then we have detailed design, which would have the logic of the modules in the high-level design. So we have to perform three main tasks. We have to identify the architecture design. Once the architecture design is completed by identifying those components and connectors that should be in the system, based on the requirements that have been selected or like retrieved from phase one, we take those architectural design and build on the top of it the high-level design that would identify those modules and data structure to implement the architecture. And finally, we have the detailed design that provide the logic of the modules. Most methodologists in modern software, they focus on the architecture or the high-level design. The outcome or the output of the design phase are architecture, description, logic, design documents. The third phase, so now we have collected the requirements from the customer. We have provided a definition of the problem that we're trying to solve. We have designed, and we have provided design for such problem. Now it's time to convert the design into code according to a specific language. So coding is all about the conversion of the design that we obtained using the design document generated from the design phase. We have to convert it now into code, and it's mainly language-based. The goal is to implement the design with simple and easy to understand code. Keep in mind, line of code is used for cost calculation. So the simple and easy understandable code that you will end up with more modularity, for example, will end up that you will have a software with less cost or effective cost. In coding phase, we know that it affects mainly on the testing and the maintenance phases as well. Because if you do have well-written code, that means you are reducing testing and maintenance effort. The outcome at the end is just a code. Finally, after we code on the software by a certain programming language, now we have to test the software and do quality assurance. In order to perform a testing phase and test the quality of the software, we have to know that defects are introduced in each phase. Those defects must be found and removed to achieve high quality softwares. The goal of phase 4 is to identify most of those defects. We know that it's a very expensive task and must be planned very carefully and must be probably executed in a well-defined process. Outputs of the testing and quality assurance phase include testing plans, testing results, as well as the final tested, which we really hope to be reliable, code. After we test the software and it's ready for deployment, this is phase number 5, which is the delivery phase. It's mainly about what the operation group would do. It varies based on the distribution model. We can see shrink-wrapped software, or we could see in-house software, web-based software, or even software as service. From the user's perspective, you might be surprised that the delivery of the software, it's important as a design phase. So the delivery phase is actually has the same importance importance as the design phase from the user perspective. So now, after I have covered the major phases of a software development cycle, let's watch this video together. It's an animated cartoon that will summarize the software development lifecycle process.
In order to understand what a software tester or quality assurance analyst does, you first need to understand the process by which the software is conceptualized, developed, and maintained. This process is known as Software Development Lifecycle, or the SDLC. There are 7 key points to understanding the software development lifecycle. Phase 1, planning. Phase 2, requirement analysis. Phase 3, design. Phase 4, implementation and coding. Phase 5, testing. Phase 6, deployment. And Phase 7, maintenance. So it all starts with this guy, the customer. He's the guy that has the business idea for our invoice application and the money to get it started. He's going to reach out to multiple different tech companies until he finds one that he likes. Finally, he's going to meet our company's product owner or our project manager. They're going to discuss terms of their agreement, sign a deal, and accept the project. This will move us into the next phase, planning the requirements. Together, the customer and the product owner will outline the requirements of the application. Let's imagine that the requirements that they've both agreed upon are as follows. 1, user registration. 2, login. 3, log out. 4, the dashboard landing page, and so on and so forth. Throughout this course, we'll be running multiple iterations of the SDLC to which new requirements and new features will be added. Now that we have the outlined requirements, let's take them and move on to the requirement analysis phase. Here's our team: operations, developers, product owners, and testers. We'll all meet up in an office for a few hours and define each outlined requirement and give more planning details. Let's start with requirement number 1, user registration. We'll need a username input field, a password field, a checkbox to accept the terms and conditions, a submit button, and the ability to save the user into our database. Then we'll move to requirement number 2, the login. We'll need a login page to allow returning users to log back into our system. For this, we need another username input field, a password field, along with another submit button. From this, we'll need to read the user's information out of the database and log them into our system. Requirement number 3 will require a logout button, usually located around the same area where the user was logging in from. When they press the logout button, it should clear their session out of the browser to prevent other people from returning and logging back into their account. Finally, requirement number 4, the dashboard. This will essentially be the home page of our application. After a new user is registered, they should be redirected to the dashboard. Also, when the user logs in with a returning account, they should be redirected to the dashboard. For our first SDLC, I will keep the requirements easy. In upcoming videos, we'll dive further in with much harder customer requirements. Once all of the requirements have been analyzed by the team and defined, the product owner will take all the defined requirements and create tickets in a project management system. From here, we'll move into the design phase of the SDLC. The design phase takes all the requirements and starts to plan the product. The design phase may include the business rules, the user interface layouts, color schemes, what programming languages to use, frameworks, system server design, database relationships, architected the application, mobile aspects, supported browsers, and much more. Next, we'll discuss the implementation and the coding of the application. The implementation and coding phase is where everything starts to become fun. The operations team will set up the physical hardware for the servers. The developers will start writing the code. The designers will continue planning the user interface. And the testers will analyze the requirements and start building test cases for their test plans. Even in this stage, testers are incredibly valuable. They start to imagine the usability of the application and see how everything flows together. Sometimes while writing test cases, they can discover things don't make sense and help redesign fundamental flaws in the early stages of the application. Next up, we'll be discussing one of the most important phases, which is the testing phase. In order to understand what a software tester or quality assurance analyst does, you first need to understand the process by which the software is conceptualized, developed, and maintained. This process is known as Software Development Lifecycle, or the SDLC. There are 7 key points to understanding the software development lifecycle. Phase 1, planning. Phase 2, requirement analysis. Phase 3, design. Important phases, which is the testing phase.